All right, ladies and gentlemen, today's class recording has started. So yesterday, we introduced the concept of free fall. What is our definition or what is our description of something that is in free fall? Eric, go ahead. Gravity is the only force acting on the object. And when gravity is the only force acting on the object, what happens to it? Good. Not always. Not always. I want to go something a little more general than that. That is how we describe it. If we look at its motion, an object that is in free fall will do what? In a very general sense. Ellen? Not always. We'll see that today. So yesterday when we did the volleyball graph, it will accelerate. How much will it accelerate, Eric? 9.8 meters per second every second, right? Yesterday when we introduced the concept of free fall, we did the volleyball, right? The volleyball went up in the air and then came back down. It slowed down, it changed directions, and it sped back up on the way down. Good? That whole time, it's in free fall. Well, not exactly because we had air resistance, but an object that is in free fall will experience a constant acceleration of 9.81 meters per second squared. Okay? Good there? Now, Frank, and we got kind of other people too. For certain instances, we see that certain things happen. If we drop two objects at the same time, what will happen? They're going to land at the same time, regardless of their mass or their density or what they're made out of or whatever, right? So yesterday we saw the video of physicist Brian Cox at the NASA research facility in Cleveland, and he dropped a bowling ball and a feather. And they, when we got rid of the air in the big test facility, they hit the ground at the same time, right? So apple and feather on the right-hand side, if we can get rid of the air resistance, they would fall at the same rate, accelerate at the same rate, 9.81 meters per second squared, and then hit the ground at the same time. We saw the same thing in the video of astronaut David Scott, who was on the moon. He did that experiment, not with a rock and a feather, but with a hammer and a feather. Same thing. When we say gravity accelerates all objects at the same rate, that's true, but what that rate is depends on where we are, right? Here on Earth, that rate is 9.81 meters per second squared. But on the moon, and here we write this, right? G sub m, because we said lowercase g represents the acceleration of gravity, that acceleration is only 1.6 meters per second squared. So while both of the objects on Earth experience the same acceleration as each other, and both of the objects on the moon experience the same acceleration as each other, different locations experience different rates of acceleration. Okay? Good there. We okay with that idea? Okay? So, that then leads us to this. Right? Gravity accelerates all objects on the same rate. Gravity on Earth causes a uniform acceleration of 9.81 meters per second squared. We said uniform and constant mean the same thing, right? We saw yesterday from the graphs, oh, by the way, let me show here. I meant to show you guys this, so I'll show you this right now. That means like it mimics the angular. Stand by. So I remember when I was doing the volleyball yesterday, and it was just like the graphs were coming out really sucky, you know? After you guys left, I was like, oh, I should change one of the settings on the motion detector. And when it happened, when I changed that setting on the motion detector, So. This is going to be great on the recording. See, like, yeah, like that. It's a lot better than the graphs we were looking at yesterday, right? So, all right. So here we talked about these two pictures, right? And how the position graph is showing something going up and down. The velocity graph by the fact that it starts above the x-axis and goes below the x-axis. That means it was going up, now it's going down, right? All those things. But if I change the velocity graph to acceleration, you'll see that there's a part right through here, and this isn't the best one because of the settings that I had. There's a section of this acceleration graph that's fairly flat, even though the object is going up and down, right? Gravity acts on things regardless of what they're doing. We said that on the velocity graph, during this section of the velocity graph, the object is slowing down, right? Does that make sense from our, right? Because which way is gravity acting on it? Downward, but which way is it moving? Upward. So if something's trying to go this way, but something's pulling on it this way, what's going to happen to that object? It's going to slow down, right? Eventually, once it slows down, it'll start moving in that direction, but first it needs to slow down before that, right? So this constant acceleration of gravity affects all objects, not just when we say something is in free fall, that doesn't necessarily mean it's going down. It just means it's being acted on by gravity, all right? So the next page of your packet has a couple of questions to try and introduce you to this concept, okay? So let's go through some of these, okay? First, I'm going to introduce you to the best ant in the whole world, okay? And her name is Aunt Minnie. And why is she the best ant in the whole world? Because Aunt Minnie gives you $10 per second for 4 seconds. We all need an ant to give us $10 a second. Is this correct? I think you would agree, right? So hopefully this question isn't too terribly difficult, right? If Aunt Minnie gives you $10 per second for 4 seconds, how much money are you going to end up with after 4 seconds? $40. Okay. All right. Before we answer the next question, I'm going to introduce you to a new place in the universe. Okay? That new place is anti-Earth. Okay? It looks a lot like Earth. Right? Similar size, similar shape, similar land formations. But there's one difference. And you'll see why this difference is going to be helpful to us. All right? Here on anti-Earth, all right, there is gravity. And that gravity causes a constant acceleration. No. Okay? It makes sense, but that's not what I'm going to do with this, all right? So, but here on anti-Earth, right, the acceleration of gravity is 10 meters per second squared, not 9.81. Does that make sense? Okay. Are we okay with this? Yeah. All right. You'll see why I'm going to do this in just a second. Okay. So let's say for the next question, a ball is dropped from rest, but that ball is dropped on anti-Earth, not regular Earth. Okay. Yes. And it picks up speed at 10 meters per second. After it falls for 4 seconds, how fast will it be going? 40 meters per second, right? Picking up speed at 10 meters per second is giving us what value? That's describing the what? That's describing the acceleration, right? It's how much does the velocity change every second. Okay? All right, next. You already have $20, okay? And Uncle Harry, not as, you know, he's not bad as he's not bad, right? Yeah. Okay. He only gives out $10 a second for 3 seconds, though. All right, so you know, if you have a chance, go to Aunt Minnie, but you know, Uncle Harry's not a bad option either, right? So, if you already have $20 and Uncle Harry is giving you $10 each second for 3 seconds, how much money are you going to end up with after those 3 seconds? $50. Is the rate at which you are picking up money different for Uncle Harry than it is for Aunt Minnie? The rate at which you're picking up money, is it any different? No. You're picking up money at the same rate, regardless of whether you start with $0, like when Aunt Minnie was giving you money, or if you start with $20, like Uncle Harry's giving you money, right? You're still picking up money at 10 meters or $10 per second. Good? Okay? All right. Next. Anti-Earth. Okay? A ball is thrown straight downward. So instead of just letting this object drop like this, I'm going to throw it downward. Right? That was venom right there. All right. So I throw it downwards, and it's traveling 20 meters per second when it leaves my hand. But as soon as it leaves my hand, what starts happening? It accelerates because of what? Gravity. The fact that it's already moving when it leaves my hand does not change the fact that gravity causes a constant acceleration of 10 meters per second squared on anti-Earth. Right? Does that make sense? So, if it's already going 20 meters per second, but it's picking up 10 meters per second every second, how fast is it going to be going after 3 seconds? 50 meters per second. All right, good there. Your mom takes notice of the fact that your great Aunt Minnie and your great Uncle Harry are giving you tens, 1 per second, and it's like, no, you're not going to take their money like that. All right. So it doesn't say this here, but in question number 5, your mom, it should say you have to. It would say your mom makes you, right, pay back Aunt Minnie $10 for every $10 every second. All right. If you have $50 and you have to pay Aunt Minnie $10 a second, how long is it going to take you until you get down to 0? 5 seconds. Okay? So, number 6. Just like the picture on the previous page that we looked at, right? There's a guy shooting an arrow up into the air, right? But he's on anti-Earth. Okay? So, shoots an arrow up in the air, and it says that that arrow is going 50 meters per second. But as soon as it leaves his bow, what starts affecting it? Gravity. Gravity on anti-Earth causes an acceleration of what? 10 meters per second squared. Or 10 meters per second. But in the case of this arrow, just like in the volleyball we saw yesterday, if the arrow is going upward and gravity, even on anti-Earth, is pulling it downward, right? What's going to happen to the velocity of that arrow?
It's going to slow down, and then it's going to speed up.
Well, let's just talk about the upgrip, right? It's going to slow down, right? So, if we've shot the arrow upwards with 50 meters per second, when does it run out of speed? How long is it going to take? 5 seconds. The velocity still changes by 10 every second. Just what kind of change is happening? Increasing or decreasing? Decreasing, right? Gravity's still pulling it downward even though it's going upwards. So it would take 5 seconds for that arrow to run out of speed. That being the case, what will its speed be at 5 seconds? 0 meters per second. Does that make sense? That being the case, where is the arrow now? No. Has it started coming down yet? No. So how would we describe the arrow 5 seconds after we shot it? Sammy? It's still, its instantaneous velocity is 0. Where, what were you going to say, Julie? Was that what you were going to say? Or? Good. It's at the highest point that it's ever going to be. Okay? After 5 seconds, here, let's do this. Okay? So, when we shot the arrow, right, it was going 50 meters per second. And then we could draw its location, and they might look like this, and it might look like this, it might look like this, it might look like this, and like this. Does that make sense? Why I drew those red dots where they were? All right? So, that means, let's see if I did this right. 1, 2, 3, 4, 5. Yes. Right. So up here, the velocity of that arrow is 0. It's at the very, very top. Okay? Here's a tricky question. Okay? Is the arrow still in free fall? What's our definition of free fall? Let's do it. How many people say yes, the arrow's in free fall? How many people say no, the arrow's not in free fall? How many people don't know and are scared to vote? Okay. So, what's our definition of free fall? Even though that arrow is stopped, is gravity still acting on it? Yes. So is it still in free fall? Yes. Okay? And one of the consequences of free fall is that objects experience an acceleration of 9.81 meters per second squared. Good? Does that make sense? All right. So, question. This is the kind of question that, I don't know, might show up on a test on Thursday. Maybe. Just saying. Maybe. If an object has 0 velocity, does it have 0 acceleration? If an object has 0 velocity, does it have 0 acceleration? Lots of people are writing down. I'll give you the first crack at it. If an object has 0 velocity, does it have 0 acceleration? All right. Ellen, what's your answer?
I say
No.
no.
No is the correct answer, by the way. Okay? Now, explain.
Because whenever it's on Earth, it's always going to be acted upon by gravity.
Good.
And even on that very small moment of when it balances out and has 0 velocity, it's still accelerating back down to Earth.
Good. Let's go back to our questions, right, at the beginning. Where is the object? What is it doing? What's it going to do next, right? Velocity tells us what is the object doing. At this very moment in time, at the top of the motion, what is the object doing? If its velocity is 0, what is the object doing? not moving. But acceleration tells us not what's happening now, but what's going to happen next, right? So Alec, just because the arrow is stopped right now, like you said, what is it going to start doing immediately after that?
Accelerating.
Well, let's go with, it's technically at that point it is still accelerated, even though it's stopped. It's stopped now, but what is it going to start doing immediately after it stops?
Start heading back out.
Good. It's going to start moving again, just in the other direction, right? Remember, acceleration tells you the future, what's going to happen. Even though it's stopped right now with zero velocity, that doesn't mean it's going to stay stopped. All right? Does that make sense? Okay. Good with that? Next question. If something has zero acceleration, does that mean it has zero velocity? If something has zero acceleration, does that mean it has zero velocity? How many people say yes? Zero acceleration means zero velocity. How many people say no? Zero acceleration doesn't mean zero velocity. How many people are confused and not sure how to answer that question? All right. Again, let's think about what these things tell us, right? Velocity tells us now, acceleration tells us next, right? Something that has zero acceleration, what does that mean? Good. Good. The velocity isn't changing. It doesn't mean there's no velocity. It just means it could, but it doesn't necessarily mean that it has to be, right? So just because the acceleration of an object is zero doesn't mean that its velocity has to be zero. It just means that its velocity isn't changing, right? So, Frank, your water bottle that's sitting right next to you. No, leave it there. Okay? What is its velocity? Zero. What is its acceleration? Zero. Because it's sitting there and it's not going anywhere. Right? We talked about the ball at the top of the motion, the very, very top. What is its velocity? Zero. But is its acceleration zero? No, because it's stopped for an instant, but it doesn't stay stopped. Right? Finally, a car on the highway that has the cruise control set. Are we familiar with that? Right? The cruise control keeps the car going, right? Does it have zero velocity? No, it's moving. But does it have zero acceleration? Yes. Did you say that just because Jack said it?
Yeah.
What you said originally was appropriate here. A car on cruise control has what kind of velocity? Constant velocity. Constant velocity means what? No. Constant velocity means what? When we say something is constant, what does that mean?
I don't know.
What does constant velocity mean? This means that its velocity is the same, right? And if the velocity is the same, what is it not doing? Not changing. So something that has a constant velocity has how much acceleration?
Oh my gosh.
No.
Oh.
Listen to Frank.
Go ahead, Frank.
Zero.
It has zero acceleration because it is not changing. All right? Yes, Sammy. Aha. What if the car goes around a curve? Is it accelerating then? Yes. It's a different type of acceleration. It's not positive acceleration. It's not negative acceleration. We actually call that centripetal acceleration, which is a change in direction without a change in speed. Does that make sense? No. It will not be on the test. So, okay. So, what? It was, like, conceptually, that was a question on the quiz. Like, I could ask you conceptually, can something change, can something accelerate without speeding up or slowing down? That would be appropriate, but that term, centripetal acceleration, will not be on the test. Okay? All right, good there? Guess what, everybody? I think you guys might have bought yourself another day on the test. We might push that test back to Friday because we didn't finish this packet, and I really want to finish this packet before we do our lab. So you guys may have just bought yourself another day. All right? Hey, everybody. If you're going to homecoming this weekend, or even if you're not going to homecoming this weekend, be safe, be smart, take care of each other. Come back and see us on Monday, please.
What is up, my dudes?
Good thing we